Nuclear radiation and radioactive decay can be both one of the most interesting and most challenging aspects of physics for students to grapple with. With the invisible process of decay compounded with the seemingly complex maths of half-life, students can often leave the classroom with misconceptions about this difficult topic. However, Marie Curie, the pioneering scientist who laid down the foundations for all knowledge of radiation and the first person to win 2 Nobel Prizes, said, "Nothing in life is to be feared. It is only to be understood." In order to help our students secure this knowledge, we should aim to provide clear context to which they can anchor the conceptual content. For example, discussing with students the wide-ranging applications of nuclear radiation in day-to-day life, from the industrial uses in the quality control process for maintaining aluminium foil thickness, to smoke detectors in their own homes. Combining these examples with real stories, such as the poisoning of Alexander Litvinenko or the radium girls, should ensure that students are engaged with this part of the physics, and what might seem challenging to them at the start will become much clearer. I'm Ben Dickens, an IOP schools-based coach, and in this short series of videos we'll discuss some of the models and techniques we can use with our students to help them grasp the trickier concepts. We can begin by having a look at what we'll be discussing in this episode today. Episode 1 will allow us to discuss the difference between irradiation and contamination. We will also discuss the different types of ionizing radiation that we teach to our students. We'll also look at the ways that we can model these decay processes to clearly communicate the physical changes the nucleus undertakes during what students need to understand as a spontaneous and random event. Let's first start with a common area of difficulty in the classroom and within society as a whole: the difference between irradiation and radioactive contamination. Irradiation is the process of exposing an object to nuclear radiation. The irradiated object does not become radioactive. This is a common misconception and isn't exclusively held by students, but has also made its way into society as a whole. The term irradiation conjures up images of Chernobyl and hazmat suits, thus luring students into a false understanding. Careful irradiation of foodstuffs, for example, is a positive thing. Irradiating a strawberry, for example, kills the bacteria on the food, helping preserve it longer. The strawberry does not become radioactive. Contamination is the unwanted presence of materials containing radioactive nuclei on other materials. This includes the radioactive nuclei being on or inside living things. When contaminated, an object has an increased exposure to radiation as the contaminating material continues to decay. The risk related to contamination is determined by the type of ionizing radiation being released and the activity. Let's find out from Sue how we can demonstrate the difference between irradiation and contamination in a clear way that students will be able to grasp.
Thank you, Ben. So let's model irradiation and contamination using a party popper, strawberries and sheep. Firstly, irradiation. Here the party popper represents a radioactive material like cobalt-60 in a sealed container. It can be used to irradiate soft fruit like strawberries. The source emits gamma radiation, which destroys any bacteria, viruses or insects on the food. The gamma radiation will also irradiate the food, causing some small chemical changes, but it does not make the food radioactive. The strawberries have not been contaminated. Medical equipment like this syringe can also be irradiated. The gamma radiation kills any bacteria on the syringe, making it sterile until the package is opened. The syringe has been exposed to the gamma radiation, but it's not come into contact with the radioactive material. That's still in the sealed container. Now let's think about contamination. Now the party popper is representing the Chernobyl nuclear power plant. When the explosion occurred at Chernobyl in 1986, the resulting fire sent a huge plume of radioactive material into the atmosphere. This caused extreme devastation over an extensive area, and even now some of the surroundings remain contaminated. The plume of radioactive material was transported by weather systems over large parts of the Western Soviet Union and much of Northern Europe, including the upland hills of Wales. This radioactive material settled on the Welsh hills and was ingested by the sheep as they nibbled away at the grass. In this way, accumulations of radioactive material built up in the bodies of the sheep, therefore causing the contamination of our food chain.
Now let's talk about the three types of ionising radiation that we discuss with our students: alpha, beta and gamma. The general case for all three decay types is that each represents changes in the nucleus, manifest by ejected alpha or beta particles and/or gamma waves. Being able to simulate these decay types for students is vital in order to help support the understanding of the process. Our simulations should reflect several of the key points about each radiation type. We can start with alpha decay. The nucleus of the atom emits an alpha particle. This particle is made up of 2 protons and 2 neutrons, giving it the same mass and charge as a helium nucleus. Losing 2 protons and 2 neutrons from the nucleus reduces the relative atomic mass of the atom by 4 and reduces the atomic number by 2. Next up is beta decay. The nucleus in this case emits a beta particle when a neutron decays into a proton and an electron. This fast-moving electron is ejected from the nucleus as the beta particle. The loss of this small particle therefore has no effect on the mass of the atom, but the change of a neutron into a proton does increase the atomic number by 1. It's really important to stress to students that the ejected beta particle is not an electron from one of the orbitals, but is in fact being ejected from the nucleus itself. Finally, we come to gamma decay. Gamma radiation is an electromagnetic wave which is emitted from the nucleus as it decays to a lower energy level. This can be expected to happen alongside alpha and beta decay. As gamma radiation is a wave and not a particle, it has no effect on either the relative atomic mass or of the number of the protons in the nucleus. A misconception students often have is that alpha particles and beta particles are radioactive. This is not the case. The nucleus is radioactive as it emits radiation types. Alpha and beta particles do not emit radiation. The particles themselves are stable and ionising, but not radioactive. Armed with our understanding of the 3 radiation types, we can model radioactive decay for students in a way that ensures they build strong prototypes that they can refer back to during exam questions and other applications of the knowledge. We could use plasticine balls to allow students to build model nuclei and ask them to show the changes in the nucleus after certain decay types. This will allow students to tangibly see, for example, the difference made when a nucleus loses an alpha particle. Alongside our models, we can use decay cards so that students can construct decay equations in a way that shows them quick changes being made on each side of the equation. Here is an example of alpha decay as uranium decays into thorium. Students can select the appropriate cards to model the decay in a question. Or, like in the case here, we can give students the parent and daughter nuclei and ask them to identify the missing radiation type. Here you can see the same technique being used to construct a beta decay. Here we can identify clearly to students why it is that the atomic number has increased and can discuss the mathematics of balancing both sides of this equation. The decay card should be used alongside other models for students to translate what they see in the model into the decay equation that is used to describe it. Another really interesting model to use in the classroom is the balloon model. Let's head back to Sue to find out more.
Thank you, Ben. I'm using this bunch of balloons to represent the nucleus of a radioisotope. The blue balloons are neutrons and the red balloons are protons. Firstly, I can model alpha decay by removing 2 blue and 2 red balloons. That's 2 neutrons and 2 protons, or the nucleus of a helium atom, or an alpha particle. I can then see that my original nucleus has seen the mass number decreased by 4 and its atomic number decreased by 2. Now let's model beta decay. Watch carefully as I pop this blue balloon. Oh, so the blue balloon has popped, revealing an inner red balloon and emitting a yellow counter. And this is representing a neutron turning into a proton and emitting a fast-moving electron or beta particle. For beta decay, we can see that the overall mass number remains unchanged, but the atomic number has increased by 1. And finally, to model gamma emission, we can shake the balloons to represent the nucleus in an excited state and then stop the shake following the emission of a gamma ray to represent a less excited state. Notice that the mass number and the atomic number of the nucleus has remained unchanged for gamma emission.
So that brings us to the end of episode 1. I hope you found it useful and that there are techniques that you can take away with you to use straight away in your classroom. Join us in episode 2 to discuss how to model and measure half-life, how we can teach students to interpret decay graphs, and what uses of radioisotopes are best to share with our students to secure their understanding. Don't forget the other CPD videos available at spark.iop.org. Thanks for watching today. Goodbye.